in this video, we continue our list of examples of morphisms of projective varieties with a particular example called projection from a point, which is super important in many classical computations. And we're going to see a nice application at the end of the video. So to state the projection from a point, the input is that we choose a point. Let's choose it to be this origin of u0. So somehow this is the point 1, 0, 0, 0, 0. And the affine coordinates on u0, this is just the origin 0, 0, 0, 0. So this is a point in Pn. And then we choose a hyperplane, which is in this case the hyperplane at infinity, the vanishing locus of x0, which we know is isomorphic to Pn minus 1. Then we claim we get a map from Pn minus this point A to Pn minus 1, which takes this vector with homogeneous coordinates x0 to xn and just removes the first coordinate x0, just remembers x1 up to xn. So the first statement here is that this is indeed a morphism. We see its components are given by homogeneous polynomials of the same degree. And where is it defined? Well, it's defined away from the vanishing locus of all these components. The vanishing locus of x1 up to xn is just exactly this point here, because you see, if you require all of the last n coordinates to vanish, then, well, the first coordinate is some non-zero scalar. You can scale it to 1, and then you get exactly this 1.8, where it would not be defined. So a priori, this just looks like a standard application of the lemma that we had. But then we can also provide some geometric interpretation having to do with this picture. Because, well, let's give ourselves any point x with some coordinates here in Pn minus 8, so in the domain of this map. Then the claim is there is a unique projective line, LAX, so a projective linear subspace of Pn of dimension 1 through both the point A and the point X. So this is this red one here. And we can actually write down what LAX is. The claim is, as I said, this line is just given by all homogeneous vectors like this, where S and T are elements of P1. So, I mean, where does this representation come from? So, first of all, I mean, to see this, let's look at this representation of Pn, or this map from K n plus 1 minus the origin, right? This is just a standard map which sends a vector to its equivalence class. And then a linear subspace, LAX, of dimension 1 in here. Under this pre-image, I mean, linear spaces are just the images of linear spaces here. So it would be a linear space inside Kn plus 1. And then the fact that it goes through A and X means it's a linear space of dimension 2, which should contain both A and X here in the pre-image. But there's a unique one, which is just the linear span of A and X, right? So somehow A, X are not the same vector inside Pn, so they are not linearly dependent. They're not, one is a scalar multiple of the other. And so this means that their span is a two-dimensional space here, which then gets sent this one-dimensional thing. And you see, this is a two-dimensional space minus 0, and we take its elements up to scaling. So this looks like the construction of P1, which is also k squared minus 0 up to scaling. So maybe then it's not a surprise that that the answer here, LAX, is basically isomorphic to P1. And how do we get this concrete representation? Well, A was this point here, X was this point. And then if you take the linear span, well, these things are exactly the elements of this linear span, because we can take basically T times this point here. And then the first coordinate, we can, by a multiple of a, we can choose whatever we want. So we can choose this to be s, and this time these t times xi. Okay. So maybe, I mean, if you want to convince yourself of this, maybe you can pause the video, just stare at these equations, maybe write something down for yourself until you're happy with this representation. So I know this video contains a lot of formulas and a lot of claims, so it might be useful to occasionally stop to verify it for yourself. Okay. But so we started with this picture, we had a and x, and then we found a unique line here. And then the claim is this map f of x, I mean, f sends x to some point inside Tn minus 1, the line at infinity. And the claim is this point is exactly given by the intersection of this, let's say, hyperplane at infinity and this line here. Because, I mean, doing this intersection is kind of fine on the formula level because these are the elements of LAX. And then we intersect with the vanishing locus of the 0th coordinate. So, but this in this representation is just corresponds to setting s equals to 0. And then the remaining term is just this x1 up to xn. We can choose t to be 1 in this case, for example. And then we saw this hyperplane at infinity. To identify it with Tn minus 1, we just kind of remove the first coordinate, and then we get this vector x1 up to xn, which is exactly f of x. Okay. So with this interpretation, we see this map here just takes any point x, which is not a, takes this line here, intersects it with L, and then sends it to the corresponding point in L, which is isomorphic to Pn minus 1. This is why it's called projection from a point. So if you imagine a light source here, then the shadow of this point x on this hyperplane here would exactly be this f of x. So we get this projection from A to this linear subspace L. Then the next remark is we started with a particular A and this particular hyperplane here. But in fact, it works for a general point A and for a general hyperplane not containing A, like this. And the idea here is, well, you can either do the same recipe. You can compute the line from A to X and then intersect it with L, and then you get an intersection point and write down the corresponding map. This is fine. What you can also do, last time we have seen these projective automorphisms, which are basically change of basis inside Kn+1 by some general linear element. And what you can then do, if you're given A and L, this means you're given a vector, and then you're given an n-dimensional subspace of Kn+1, not containing this vector. Then you can choose an element A in GL n+1, which sends this vector to the vector 1, 0, 0, 0, and sends this n-dimensional plane to the corresponding vanishing locus of x0, which is a plane inside Kn+1. Okay? So you can kind of move those things by projective automorphism, and then there you know what the projection should be, and so you can get the projection from the given A to L by composing with this isomorphism. Okay. Again, you might want to pause and convince yourself of this. And so we can now project from any point to any linear subspace of codimension 1, which doesn't contain this point. And then there's a cool thing which we can do when we don't project from kind of all of Pn minus A, but we project from some subset there. And so to see what we mean by this, first of all, note in our definition of this projection morphism, we had to exclude A. And in fact, it's not possible to extend it over this point. The reason is when x moves around, we always have this f of x, but then as x starts to approach this A, you see this intersection point really depends on the direction in which we approach A. So now if we approach it from different angles, we would get different intersection points. And so there's no continuous way to extend it to A. However, in some specific examples, when we restrict to some subset X of Pn, a suitable closed subvariety containing A, then sometimes we can extend F over this X. And in the rest of the video, we're just going to do one concrete example of such X. So we take N to be 2, we work in a projective plane, and take X to be this hypersurface cut out by x0, x2 minus x1 squared. This is a hypersurface, it's cut out by a single equation, and it's quadratic, so it is actually a conic. And this contains the point A, which is 1, 0, 0, because if you plug in x1, x2 equals 0, you get 0 here, okay? So in the picture until now, we have the ambient space P2, we have X, this vanishing locus here, and we have A inside here. And then we claim that we get a morphism from X to P1. You see here the line L at infinity, that's a morphism to P1, which sends this point here to, well, two different possibilities. If the point is not equal to A, then we take the thing that we had above. We forget the 0th coordinate, just remember x1, x2. That's fine. And now on a different patch, if we are away from this point here, 0, 0, 1, which happens to be, you can check this, this is the unique intersection point of X, the blue thing, with the line at infinity. If we're away from here, we claim that we can take the recipe remembering x0, x1. Okay. And we claim this gives a map and it's a morphism. Okay. Let's very slowly and carefully go through this and check all these properties. So first of all, the claim is it's well defined because, I mean, we need to check if you're on the overlap, or if you're both away from this point and from this point, then these two things are the same. And for this, you just observe the equation cutting out X. This is this one here. If you divide by x0, x1, then you get this equality here, right? So if x0 and x1 are non-zero, then you have this equality here of numbers. And then you see this point here, the first image point, is the same as this point here, the second image point. And if you want to go from here to here, you just scale this vector here by the quantity x1 divided by x0. I mean, clearly, if you scale x0 by this, you get x1. If you scale x1 by this quantity, you see x1, this is the same thing as x1 times x2 divided by x1. This gives x2. So you see, if you satisfy this equation here, then these things are really the same. This shows that the two possible definitions for such points here of f of x agree on this overlap. So we had a well-defined map of sets. And then it is a morphism where we have seen away from A. This here was a morphism defined on P2 minus A. So if we restrict it to X, this is a morphism. And by a very similar argument away from this point, this here is a morphism on all of P2 minus this point. So if we restrict it to X, we get again a morphism. And so we have basically covered X by two patches on which this thing is a morphism, so it is a morphism. Okay, so we have a well-defined morphism, and clearly it extends the map B, this projection that we had, to all of X. Because, I mean, here, this was the recipe that we had in part B. And then we have found a way to patch this over the point A. So while it's not possible to extend the morphism in B to all of P2 minus A, it is possible to extend it on this conic X. And then the question is here, so X varies now only along this blue part, and then you see how the intersection point here moves around. The question is, where does this A actually map? And the idea, the geometric idea is, if X starts approaching this A, then this intersection point, or then this line from A to this point here, starts converging to this tangent line here, which is the tangent line to this blue part at the point A. I mean, we didn't really define until now what tangent means, but certainly, I mean, if you look at some affine subset here, you can use the usual definition of tangent line. So I don't want to make this too precise. Certainly in this picture, you can kind of guess what it means to be a tangent at this point. And so you can check that f of A is indeed the intersection point of L and this tangent to X at the point A. And then the final thing, which is kind of cool, and which is one of the reasons why we look at this, in fact, this morphism here is a bijection, because well, now we have to show, well, it's injective and surjective. So the idea is, if you're given a point on L, then we want to show there's a unique point X on the conic lying on this line here. That's the kind of statement we want to prove. So if Y is in L, then you can write down the line L between L, A, and Y by the same argument as before. This is isomorphic to a P1. And then, so you see here, if this is Y, then, I mean, this is L, A, Y. And then we want to show there's, apart from A, there's a unique other intersection point of this line with the blue conic. And to do that, well, just take the equation cutting out the conic and restrict it to LA. Then this is a polynomial on this P1, and it's a polynomial of degree 2, because this was of degree 2. And so there's an exercise, which is in general an important exercise, namely, if you have a non-zero homogeneous polynomial, which you see as an element of SP1, homogeneous of degree D, then F has D zeros on P1 if you count them with multiplicity. Now, I mean, you know on the affine line how you can compute the multiplicity of a given zero, because you just write the polynomial, you factor it into linear factors with some exponents, and then the exponent gives you the multiplicity of the zero. And then if you cover P1 by the two usual affine patches, you can use this recipe to compute the multiplicity of a zero. So taking a step back, what are we doing? We have a polynomial homogeneous of degree 2 on this P1, and then the exercise tells us it should have two zeros counted with multiplicity. One of them is always as x equals a, right? Because a satisfies this equation. It lies in this line. So this is always one solution. And then the other solution is exactly at the unique pre-image point here. So somewhere here you have y. This is LAY. And then there's exactly two solutions. And certainly, I mean, in this picture here, if you move the point y around, then you basically get every single line through A, and you see all of these lines have the property that they intersect. They intersect the circle in one more point. Note this particular line here between A and f of A, this becomes the tangent, and then this kind of second point counted with multiplicity is just A again. So then you have a kind of double zero at A. And this shows that this point here is mapped to A. Okay, so the summary so far is that we have shown it's a bijective map. Now this here was the geometric argument, saying that if you fix this point and this point, there's a unique other intersection point, which is then the inverse. But you can also make it easy for yourself. You can also just write down what the inverse map is. So somehow if you see this line L as a P1, then the inverse map here is just given by this map y0, y1 maps to this thing here, y0 squared, y0, y1, y1 squared. So if this was too nebulous for you, you can also just write down this map here and then show that if you compose it with f in the two different directions, you get the identities. Okay, that's the other possibility to see that f is bijective. And so what we have done is we have written down this morphism here from x to p1, and we have now seen that there's an inverse morphism from p1 to x. And you see, this is not just a map, but by the same lemma that we had before, it's also a morphism, because the elements are given by homogeneous polynomials of degree 2, and this morphism is defined everywhere. So this shows x is actually isomorphic to p1 as a pre-variety. So we have started with one concrete conic, and we have shown it's isomorphic to P1. This is basically the first non-trivial isomorphism of projective varieties that we have seen. This particular conic is isomorphic to P1. And it turns out, and this is kind of the last thing that we want to do, is that this works in general. This doesn't just work for this conic, but in fact it works for arbitrary irreducible conics. So let's say x inside P2 is any irreducible quadric curve. So in other words, a projective conic. And let's assume, and that's kind of important here, that the characteristic of our base field K is not equal to 2. Then what we can do is we can take the intersection of x with A2 with a standard patch. Then we get an affine conic. And in that exercise in Gartmann's notes, you can show that any affine conic is isomorphic either to the vanishing locus of this x2 is equal to x1 squared, usual parabola, or this vanishing locus of x1, x2 is equal to 1, which is the usual hyperbola. Okay, so any affine conic can be put in one of these forms. And it can be put like this via some linear transformation of coordinates, plus maybe a translation from A2, just translating by a fixed vector. Now, I mean, if you haven't done this exercise, this is very similar to taking, like in high school, if you have a quadratic function, then by translating it and scaling it, you can always bring it to the standard parabola form. And this is very similar, except you don't just have a function, but you have kind of any equation of in these two variables of degree 2. But basically the same kind of coordinate manipulations that help you there will also help you put this in these standard forms. On the affine part, you can always either transform it into the parabola or the hyperbola. And then the next claim is, this was happening in A2, but this combination of linear transformation plus translation, this gives you a map called an affine map from A2 to A2. And the claim is this affine map in fact extends to projective automorphism from P2 to P2, right? A2 sits in here, A2 sits in here. And the claim is that this kind of linear transformation plus translation, if you look at the coefficients, you can then just write down a projective automorphism like a matrix, a 3x3 matrix then, which extends this. And then this thing here, hence x intersected A2 to one of these two possibilities, right? And so up to this projective automorphism, we have that X, which is the closure of its affine part, as we have seen in previous videos. Well, either via this projective automorphism, or I mean, you can see it like this, it is given by either the projective closure of this or the projective closure of this. And we have seen how do we take these projective closures? We just take the thing cut out by the homogeneous part. So if you homogenize this here, you need to bump it up to degree 2 by inserting x0 here. To homogenize this, you have to bump up this term here to degree 2 by inserting x0 squared. Yeah. So via this projective automorphism, we have shown the irreducible quadratic curve x that we started with is either isomorphic to this vanishing locus or this vanishing locus. Yeah. But you see, this one here is exactly the one that we treated in part C of this example. And this one here, well, it's just the coordinates are a bit changed, but the form of the equation is the same. So this is also isomorphic to the thing that we had before. And so in both cases, I mean, up to changing the coordinates, we see x is isomorphic to this vanishing locus here from part C. And there we had seen x was isomorphic to P1. Okay. So what we did here in this example D is shown any irreducible quadratic curve in P2 over a field of characteristic not equals to 2 is isomorphic to P1. Yeah, so every irreducible projective conic is isomorphic to P1. And that's, if you want, this is the first kind of classification of some class of projective varieties we see, even though these projective conics are cut out by very different equations, up to this notion of isomorphism that we have, they all just give this very simple projective variety P1. Okay, so this shows one application of this projecting from a point, which is very useful. We have seen if we start with this conic and then project from any point on here to the line at infinity, then we get an isomorphism from the conic to P1. And that's everything for this video here. Sorry, that's not everything for this video, because to note one more thing, in this example C, we have seen that we had this map from X to P1 given by these two different recipes, depending on which of the 2 points you avoid. And this, in fact, you can see that this shows that not every morphism from X to Pn, in this case X to P1, is given by this recipe of n+1 polynomials. We have seen specifying n+1 polynomials can give you many morphisms, but in this case, there's no set of such polynomials which specifies this thing for all points. Okay. However, it is true that when you specify that domain and target should be full projective spaces, so Pn mapping to Pm, then it is the case that every morphism like this is given by n homogeneous polynomials of the same degree. And if you want, as a kind of extra exercise for this, once you have proven this, this can be used to show this claim that we had before, that the automorphism group of Pn is equal to PGL n+1k. Okay, but that is really everything for this video.